Welcome to our deep dive into the world of cycloids.
Cycloids.
Yeah, we're going to be exploring a video transcript today featuring Adam Savage.
Oh, cool.
Yeah, he's getting hands-on with some fascinating mathematical curves. Get this, he even built a track to test them out.
Wow.
We're going to unpack all of that, but first, I think you'll agree that the idea of a square wheel rolling smoothly sounds pretty impossible, right?
It does. Yeah, it seems very counterintuitive.
Yeah.
But bear with me. The transcript explains that a square wheel can roll smoothly if it's on a specially shaped surface.
Okay.
You can kind of think of it like a bumpy road where the dips are perfectly positioned for the corners of the square to fall into.
Okay.
And the Museum of Mathematics actually demonstrates this.
Oh, wow. Okay, I'm intrigued, but I also feel like we're jumping ahead a little bit.
Okay.
Let's back up to those roulettes the transcript mentions. They're not about gambling, are they?
No, not in this case.
Okay.
A roulette here is the path traced by a point on a rolling object. So, picture the little reflector on your bike tire. As you ride, that reflector traces a path, and that's a roulette.
Oh, okay.
And different shapes create different roulettes.
Okay, I see. So like a circle rolling on a flat surface makes a straight line. That's why circular wheels work so well.
Exactly.
But this deep dive is really about a specific roulette, the cycloid.
That's right.
Yeah.
A cycloid is the path traced by a point on a circle's edge as it rolls along a straight line.
Okay.
And what's fascinating is that this seemingly simple curve solves a classic physics puzzle, finding the fastest path between 2 points under gravity's pull. It's called the brachiistochrone problem.
Brachiistochrone.
Brachiistochrone.
Okay, now I would assume the fastest path is a straight line, shortest distance, right?
Right.
But the transcript says that that's not always true.
Right.
Help me understand that.
Well, think about it this way. A steeper drop means faster acceleration due to gravity. So even if a curved path is slightly longer, an object on that path might gain speed quickly enough to beat an object on a shorter straight path.
That makes sense, yeah.
Yeah.
So did someone actually figure out this fastest path, this brachiistochrone?
They did, yeah.
Oh.
A mathematician named Johann Bernoulli solved it back in 1697.
Wow.
And what's really brilliant is how he did it by drawing an analogy to light.
Light. Okay, now I'm really lost.
I know. It sounds a little wild, but stick with me.
Yeah.
You see, Bernoulli used Snell's law.
Okay.
And it explains how light bends or refracts when it travels between different mediums, like air and water.
Okay.
This bending happens because light changes speed in different mediums.
Okay, I kind of remember that from science class.
Yeah.
But how does light connect to a falling object?
This is where Bernoulli was so insightful. He realized that a falling object's increasing speed is like light's changing speed in different mediums.
Whoa.
So he imagined a series of layers, each with a slightly higher speed of light, to represent that acceleration due to gravity. He applied Snell's law to this layered model, and guess what?
I'm scared to guess.
The path of least time, the brachiistochrone curve, turned out to be a cycloid.
Wow, that's incredible.
Yeah.
He used light bending to crack the code of the fastest way down. I'm starting to see why this cycloid is so special. But the transcript mentions that Adam Savage actually built a track to test this. It's making me want to see this in action.
It really is quite something to see this abstract concept come to life.
Yeah.
Shall we dive into the details of his experiment?
Yeah, let's do it.
Okay.
So tell me, what did this cycloid track actually look like?
Well, Adam built a track with 3 different paths.
Okay.
A cycloid,
Oh.
a straight line,
Okay.
and what he called an extreme curve. It had a steep drop and then flattened out.
Okay, I'm picturing that last one, like a roller coaster plunge.
Yeah.
Did they actually race things down these tracks?
Yeah, they did. And the results were fascinating.
Okay.
The cycloid won every time, even beating the straight line.
Wow.
The extreme curve was the slowest, even though it had that initial gravity boost.
That's so cool. It really proves that the cycloid shape is the most efficient for getting from point A to point B quickly. But I'm still curious, like, how does it beat the straight line?
It's all about finding that balance between gravity and distance, you see?
Okay.
The cycloid allows an object to accelerate quickly with its initial curve, but then transitions smoothly to minimize the overall length of the path.
Okay.
It's like finding the sweet spot for speed and efficiency.
I remember playing with spirograph as a kid.
Yeah.
I had no idea. I was creating complex mathematical curves.
Right.
But speaking of curves, the transcript mentions something called the tatochronous property.
Yeah, yes.
What is that?
The tatochronous property, it's another amazing feature of the cycloid.
Okay.
Tautochron means same time. And it refers to the fact that no matter where you start an object on a cycloid curve, it will always take the same amount of time to reach the bottom.
Wait, are you serious?
Yeah.
So if I start one object at the top of the cycloid and another halfway down,
Yep.
they'll both reach the body at the exact same time.
That's exactly it.
It seems impossible.
Yeah, it's very counterintuitive.
You'd think the object starting higher up would have a huge advantage.
You would think so.
But the cycloid shape compensates for the difference in starting position, ensuring they both arrive simultaneously.
Exactly.
I have to admit, I'm a little skeptical. Did Adam Savage demonstrate this on his track?
He did.
Okay.
And it's mesmerizing to watch. They released objects from various points on the cycloid, and sure enough, they all lined up perfectly at the bottom, hitting the finish line at the same time.
Okay, I'm convinced that is mind-blowing.
Yeah.
So not only is the cycloid the fastest path, but it also has this time-bending property built in. Now I'm curious, are there other types of roulettes out there besides the cycloid?
Absolutely. The cycloid is just one member of a whole family of fascinating curves.
Okay.
The transcript mentions other roulettes like epitrochoids, hypotrochoids, epicycloids, and hypocycloids.
Yeah.
They're all generated by rolling circles on or around other circles or lines.
Wow, those are some mouthful names. Are there any real-world examples of these other roulettes that we might recognize?
You bet remember spirograph?
Yeah.
The toy with the gears and colored pens?
Oh, yeah.
Those intricate patterns you can create with spirograph are actually examples of these complex roulettes.
No way. So my childhood doodles were actually mathematical masterpieces.
Exactly.
Love it. But the transcript hinted that there's even more to these roulettes, something about a visual illusion.
Yes. This one is particularly fascinating.
Okay.
Imagine tracking multiple points on a rolling circle.
Uh-huh.
Each point appears to be moving in a straight line.
Okay.
But when you look at all the points together, they create the rolling motion of the circle. It's like they're individually following straight paths, but collectively creating this seamless circular movement.
That's incredible. I'm had to look up a video of that. So we've gone from rolling circles to the fastest paths, time-bending curves, and now mind-bending visual illusions.
I know, it's amazing.
I'm starting to see the world in a whole new way. So we've covered a lot of ground in this deep dive, from simple circles to complex curves, and even touched on some pretty mind-bending physics concepts. What would you say are the key takeaways for our listeners?
Well, I think the biggest one is that sometimes intuition can be misleading.
Yeah.
Take the brachiistochrone problem. You'd naturally assume a straight line is the fastest path.
Right.
But as we've seen, a carefully calculated curve can be much more efficient, especially when gravity is involved.
It's like that saying, the shortest distance between 2 points isn't always a straight line.
Exactly.
And we have the cycloid to thank for proving that it's also amazing to think that this seemingly abstract mathematical concept has real-world applications.
Oh, absolutely. The cycloid isn't just a theoretical curiosity. It's been used in everything from designing roller coasters to optimizing pendulum clocks.
Wow.
And who knows where else we might find it hiding in plain sight.
Right. Maybe the curve of a bridge or the shape of a musical instrument. Suddenly I'm seeing cycloids everywhere. But beyond those practical applications, there's also a sense of beauty and wonder in these curves. You know?
Yeah.
It's fascinating how a simple rolling circle can generate such complex and elegant shapes.
I completely agree. There's a certain poetry to the way math and physics intertwine to create these unexpected patterns. It reminds us that there's always more to discover, even in seemingly simple things.
This deep dive has definitely opened my eyes to a whole new world of curves and their hidden properties. Before we wrap up, is there one final thought-provoking question you'd like to leave our listener with?
How about this? Where else in your everyday life might you find cycloids or other clever curves at play? I encourage you to look around with a fresh perspective. You might be surprised by what you discover.
I love that it's a challenge to see the world through a mathematical lens and to appreciate the hidden beauty and efficiency of these curves. Thanks for joining us on this deep dive into the fascinating world of cycloids. Until next time, keep exploring.